Swayam Prabha. Digital India. Educated India.
So today, moving on that, we will further focus on some more properties of this set of random variables. So today we will discuss the notion called covariance. So when we have a set of random variable, we know how to characterize the distributions. We already said that we are going to characterize that through the joint distributions, and we also want to understand some of these properties of this joint distribution. For example, if you recall, for a single random variable we had defined the notion of expectation and variance, but when we have a set of random variables, what kind of properties that we would be interested in? One thing that easily comes to mind is we want to basically understand how together they behave, like both of them are moving in. Suppose you have two random variables x and y, you want to understand whether both of them are taking in the values in the same direction, or they take value in the opposite direction, or some things of that nature, right? So let's see if we can try to capture that through some of these notions. We are going to call correlation. We are going to say, so let's say we have, let's say x and y are random variables on the same probability space. We are going to define correlation as simply expectation of their product. Then we are going to define their covariance as and the third thing I want to define as correlation coefficient. So also, like, I am inherently assuming that this random variable x and y are such that their second moments are finite, so that their variance is also finite. Okay, so if the variance is not finite, then this relation here, this definition is not so clear, I mean not well defined, so, or does not make sense. So that's why we just assume that their second moments or the variances are finite. So if you have two random variables, you can always try to characterize these values if I already know their joint distributions, right? If I know the joint distribution, I can just find the product, and using the associated joint distributions, I can compute all these things. Now, something that immediately comes to mind is, suppose x is same as y. or let's say x and y, so y is just x. So this is going to be what correlation in this case? So expectation of x square, that is basically second moment, right? And now in this case, if y is same as x, what is this going to be? And what is that? So if x equals to y, we know this is nothing but covariance of xy is nothing but variance of x. So in a way, like we are just like generalizing these notions when we have multiple set of random variables, right? Okay. Now to understand a bit more about these properties, we have this relation, what is called as Short's inequality. You people know what is the Short's inequality on a set of on a pair of vectors? So let's say A is a vector, B is a vector, their inner product is going to be norm of A vector, and is there a square root there or no? No square root there, right? So okay, so if I am going to write it as, this is going to be what? This is going to be summation ai square, and this is going to be summation bi square, right? So what is A is a nothing but a vector with components ai's similarly. So there is an analog version of this for our vectors also. So that says, if you are going to look at the expectation of this product, then this is going to be upper bound by expectation of x square y square. So if you look at the correlation of the random variables x, y, and if you look at their absolute value, that is going to be upper bounded in this fashion. And further, suppose if can show that value t holds, and only if so does not their name directly indicate what they are? At least this meaning of correlation is clear, like what is, we are calling it correlation, and what we are doing is taking the product and taking their expectation, how they are correlated. And similarly covariance, this is at the first hand we can take it as an extensions of our variance definition, right? Variance we define for single random variable, but now when we have two random variable, and if you want to centralize them by removing the mean and then look at their correlation. So for example, if this covariance is what? This is nothing but correlations of this centered random variables, right, where you are already removed the mean values. So we will try to interpret what this correlation coefficient means in a moment. So for that we need to understand, we need to have these bounds, the Short's inequalities. Okay, the Short's inequality says this, we can have an upper bound like this, and suppose at least one of these random variables second moment is not 0, then the inequality holds if and only if one random variable can be expressed as a linear, it's just a scaled version of the other random variable with probability 1 for some c, I don't know whatever that c, but as long as random variable y can be expressed, so x can be expressed as y by scaling it with some c, this is, if this holds then it is fine. Okay, now a quick look into why this relation should hold. Okay, So let's take the case of let's try to understand this. So this can be expressed as what? Expectation of x square minus 2 lambda expectation of xy plus lambda square expectation of y square. I just expanded it. So just check that if both x and y they have finite second moment, this quantity is always going to be bounded, and further this quantity is going to be greater than or equals to 0. It is going to be greater than or equals to 0, it is clear, right? Because you are squaring and taking expectation. But this is also going to be true because you can always bound that, like for any a and b this relation holds. Because of that you just expand this and then apply this result in terms, and we know that the second moments are fine. You can also argue that this is going to be finite. So just verify that. And now this is true irrespective of what lambda I choose, right? As long as lambda is finite, this relation, the second relation is true, whatever lambda I am going to set. Now set specifically expectation of xy divided by now if you are going to simplify, so for time being assume that expectation of y square is not 0, and then then this is defined properly. Then I am going to take that value as lambda. If I am going to take that lambda and plug in here, this is going to be equal to expectation of x square minus expectation of xy divided by expectation of y square. Just by plugging that lambda value and just simplifying, you get it. And this, we already know this is going to be greater than or equals to 0. Right? Now if you just going to, yeah? So I am saying that at least assume one of them is not equals to 0, right? I will just first consider a case expectation of y square is not equals to 0, and then define lambda in that case like this, and then plug in. Okay. If you want to consider the case expectation of x is not equals to 0, then just do the opposite. You just take y minus lambda x and then define it, then replace expectation of y square by x square. You can do similarly. Now if you just do this cross multiplication here and simplify, you get exactly what is called, what we are claiming as Short's inequality. Fine? Now to look into this, again it is easy to see that if suppose, let's say first assume the case x equals to cy for some c. If you now just go back and plug y equals to cx here, you see that both right hand side and left hand side match. In that case they hold with equality. Okay. Now assume that this relation holds with equality, then you can see that now you have to come up with what is the value of c that works out here, right? In this case you are just going to take that c to be this value lambda whatever you have. In that case also, then if the equality holds, then that equality is satisfied, this value of lambda. You can just check that. Okay, fine. So with this we have this relation expectation of this correlation the mod of this correlation is upper bounded by this quantity. Okay, now I have this. Now replace x by, define a new random variable, let us say x prime, which is going to be x minus expectation of x, and then y prime equals to y expectation of y. Okay, do this. Just I have defined two new random variables, right? And if they have finite second moments x and y, so does x prime and y prime will have finite second moments. Now you just plug in here. If I just plug in here, what I am going to get? Expectation of. So if you replace x by x prime and y by y prime, and then here also x get replaced by x prime, y by y prime, then what you are going to get is basically right. I have just replaced x by x prime and then introduce the definitions we have. So now if you look into this, what is the quantity on the left hand side I have? This is expectation of centered x and y, right? This is what we call, this is according to our definition, this is nothing but covariance. And what is this quantity over here? Expectation of x minus expectation of x whole square. This is nothing but variance of x. And then we have variance of y. Okay. So now with this relation, what we can right away say about this rho xy? So I know that rho xy is going to be less than or equals to 1. Okay, now let us try to understand what is this correlation coefficient means. So what we are trying to, like as I said, we have two random variables in this case and we have all these properties. What we understand is how the behavior, like is there anything we can infer when we look them jointly. So as of now our correlation coefficient, the way we are defined, we have shown that that is going to be less than or equals to 1. And now let us understand so this is like mod here, right, because I had a mod here, and so this is what I am saying is absolute value of rho xy is less than or equals to 1. That means my rho xy will be between 1 and minus 1. Okay, suppose if I find out that this correlation coefficient happens to be more than, it is going to be less than 1, but I also know that it is going to be more than 0. That is my rho xy happens to be positive. What does that mean? So let us take a simple, I am going to take two events A and B. Okay, two events that are coming from my script f. Now I am going to define a random variable x which is going to be 1 if A occurs, 0 otherwise. I can define a random variable like this, right? Whenever event A happens, I am going to take the outcome to be 1. If anything other than this happens, I will simply say 0. And I am going to define another random variable if B occurs and 0 otherwise. Now I want to understand, suppose, is there anything like if B happens, already happened, subsequently or whatever, like I want to understand, given that B has happened, does it have any bearing on happening of A? Does it make happening of A more likely or less likely? Or that what kind of information it reveals to me? So let's try to understand by evaluating this correlation coefficient here. So covariance of xy, I have written the formula here, but if you are just going to cross multiply the terms within the square bracket and expand them, it simplifies to simply okay, it just simplifies, you just do the multiplication and expand. Now I am going to take this, I am going to apply this formula on these two specific random variable I have defined here. Okay. What are the possible values the product xy can take? It can only take 1 or 0, right? It is going to take 1 when 1 occurs, right? And then what is going to be the expected value of x and y? Probability that x equals to 1, and that is the only case when that value is 1. In all the cases there is going to be 0. That's why expectation of xy is nothing but this probability into 1, but I am skipping that 1 here. Now what about this? What is expectation of x? This is going to be simply x equals to 1 and y equals to 1, right? Because I am talking about expectation, right? So how you are going to compute the expectation? Expectation is value of this and the corresponding probability. So probability are written, the associated value, when the value of this random variable with this probability is 1, right? That is exactly the expectation value. All other terms are going to be 0. Now suppose, let's say, assume the covariance is going to be positive. If this is positive, let's say, if and only if, because this is an equality, this guy is going to be positive, right? And this is positive, and this guy is positive implies, now focus on this part. So this is nothing but probability that x equals to 1, y equals to 1. Probability what I want here is x equals to 1 is greater than probability that y equals to 1. And now if you apply the conditional probability definition here, what is this? Y given x, right? Now go back and let's go back and plug in the meaning of this. X equals to 1 means A occurs, y equals to 1 means B occurs, right? Now what it is saying is, suppose let's say x equals to 1, that is A has occurred. Now what is saying that the probability that B has occurred is more than just like probability of even B that itself occurring. That means if if you know that A has occurred, that B is also occurring seems to be higher than just if you are going to ask the question whether B has occurred. So what it is telling, the covariance is telling that if the covariance is positive, that means one event happening already gives, it says that the other event happening conditioned on this is more likely than the unconditional probability. And this is what, if you are going to take this to be positive. If you are going to take this to be negative, what is that? It is going to be opposite, right? That means the condition that A event has occurred, the probability that B is occurring is now going to be less than the unconditional probability of B happening itself. So in a way, what is happening, if covariance is positive, that means one event happening has increased the likelihood of other event also happening together. So that is the meaning of covariance here. Yeah?
It does not contain equal signs.
Yeah, so if you want to,
Independence y and x are independent.
so if x and y are independent, this is going to be 0, right? So if independence means, so if it, okay, so now let's come to the case like equals to 0, covariance xy equals to 0. If covariance xy equals to 0 means what? Expectation of xy is equals to expectation of x into expectation of y. When is expectation of xy is going to be equal to expectation of x into expectation of y? When x and y are independent, right? So in that case, if x and y are independent, you already understand that happening of one will not reveal any information about the other. Only when they are other than independent, maybe one will give information about happening or not happening about the other thing. So as you already see, independence implies, so we are going to say that when the covariance are going to be 0 of x and y, we are going to say x and y are uncorrelated. Okay, when the covariance is 0. So independence implies uncorrelated. But it is in general not true that the other direction is true. Uncorrelation, if two random variables are uncorrelated, it not mean that they are independent. So you think about examples where that is going to happen. I'll just leave it as an exercise for you. Okay, we already said that when covariance is 0, we are going to call uncorrelated, independence implies uncorrelated, and then we already said that when x equals to y, covariance implies variance of the random variable x. Now, I am going to quickly list some properties, you can verify yourself, they are just like, so if you recall, when we had expectation of defined expectation, we have defined various properties of expectations, right? Like expectation is linear, expectation of a random variable if you scale, expectation also just scales, all these properties. So similarly, we can write properties of covariance. So if you have covariance of x plus y and u plus v, so now you are looking at two random variables which are themselves expressed as sum of other two random variables, right? So this is one random variable which is expressed as sum of these two random variables. This can be expressed as in terms of the covariance of this pair of random variables like this, xu plus covariance of x comma v plus covariance of y comma u plus covariance of x comma y comma v. And similarly, covariance of Ax plus B Cy plus D. Okay. So here again I am looking at covariance of two random variables, but each random variable is now affine function of another random variable. Okay. Now what will be the covariance of this? The covariance of this is going to be simply A into C, the covariance of x comma y. So it does not matter what is the value of B and D here. The intercept values in this affine function did not matter. All you need to do is what value you are scaling this value. The constant offset is not going to affect your covariance metric. Covariance like this. Okay, so often you will end up with sum of random variables. So for example, think of 5 courses, and the number you are going to get in each course is like a random variable. Let's call x1, x2, x3, x4, x5, and you want to decide what is the total sum of the marks I am going to get across these 5 courses. So in that case, you are going to define some random variable like this. Let's say x1 plus x2 all the way up to xm, and for this you want to basically calculate, let's say, the variance of this sum across your 5 courses scores. So how you are going to compute this? One thing is, yeah, is it variance of x1 plus x2 is equals to variance of x plus variance of x2? We know that expectation of x1 plus x2 is expectation of x1 plus expectation of x2, but we never said variance is also linear, right? Expectation is a linear operator but not variance. Now how you are going to calculate the variance of this? We know by definition variance is nothing but covariance of Sm comp Sm. Now does this help? If I am going to write like this, does it help? Why it helps? Because then I can go and exploit this property, right? And if I can exploit, then I know I have to only worry about a pair of random variable at any time. So if this is the case, you can just go and expand all these things. What you will end up is basically variance of xi I equals to 1 to m, then equals to j of xi and xj. You can just, I'm just like simplifying this. After you plug in this covariance term with this Sm defined like the sum of random variable. So here I have defined only for 2 random variables in the sum, right? But you can expand this if you have more than 2 here. Suppose let's say you have 3 here. How you are going to apply this formula to get it work for this sum of 3 random variables? So you can initially treat these 2 as one random variable, then we have only sum of 2 random variable, apply the formula, and then expand on this, I mean each pair. You can group so that you are dealing with only sum of 2 random variables and expand that group. Okay. So by doing this, you will end up with this formula. Please verify this. Okay, suppose I say that the scores you are going to get in these 5 courses are independent. Okay, it does not, one course is going to score of one course. So then how does this formula simplifies? So then if all of them are independent, this is going to be, so is it necessary that in this case I need to tell you that the scores are independent, or is it sufficient if I say that they are pairwise independent? So we know that like pairwise independence is a weaker notion than independence, right, across the set of random variables. So what I need here, I need a independence or just a pairwise independence? Pairwise independence will make this term 0. In this case it is simply going to be sum of the variance of each of your random variables. Okay, fine. And if I say further that all of them are identically distributed, that means they have the same x, but they are just like multiple copies. If I say they are all identically distributed, then you can just write it as like m times maybe variance of x1, because these are all going to be the same value.